Neural networks do a lot of math with a lot of data. But before we can start designing those networks ourselves and making sure all that math is set up correctly, we first need to understand how we represent that data. Specifically, we need to think about the shapes data can have. For example, we might have a single number representing a person's height in centimeters, or a list of numbers representing various features of that person, like height, weight, and age. Or maybe we have an image of that person and represent it as a grid, with rows and columns of individual pixels. And one possible way to represent a single pixel in that image might use 3 numbers, one for each of the red, blue, and green color channels. We describe these different shapes of data in terms of their number of dimensions. First, we have the smallest, simplest shape, a single value, like 1, 2.4, or negative 0.3. These are called scalars. We say that scalars have 0 dimensions. It's kind of impossible to visualize 0 dimensions, but just go with it. That's how scalars are defined. So from the examples before, a person's height would be a scalar and have a 0-dimensional shape. Then there are lists of values called vectors. There are 2 types, row vectors and column vectors. They can store the same things, but conceptually you would think of a row vector like this, 1, 2, 3, ordered horizontally from left to right, and a column vector like this, 1, 2, 3, ordered vertically from top to bottom. The reason to use one type of vector over the other is sometimes just a personal preference, but other times the shape actually affects the math you can do. Either way, a vector is said to have 1 dimension, which we call its length. So each of these 2 vectors has a length of 3. Our list from before, with a person's height, weight, and age, could be stored as a vector. Next up, we have matrices. A matrix is a 2-dimensional grid of values. We describe the shape of a matrix in terms of its numbers of rows and columns. So if you had these 2 rows of data, 1, 2, 3, and 4, 5, 6, that's 2 rows and 3 columns. So we'd say it's a 2 by 3 matrix. If you had a single number for each pixel of an image, then you could store those pixel values in a matrix. Finally, there are things called tensors. You'll hear this term a lot in this course because you'll spend quite a bit of time using a software library called TensorFlow, and it deals with all its data in the form of tensors. The term tensor can refer to any n-dimensional collection of values. So a scalar is a 0-dimensional tensor. A vector is a 1-dimensional tensor. A matrix is a 2-dimensional tensor. And anything larger than 2 dimensions, we just call a tensor. The problem is, higher dimensional data can be difficult to visualize. For 3 dimensions, you might picture a stack of matrices, but you could just as easily picture a list of matrices, or a matrix of vectors. And for 4 dimensions, you might think of a matrix where each of its entries is itself a matrix, or maybe a list or stack of stacks of matrices, or maybe even something else. And it just keeps getting more complicated as the number of dimensions goes up. The important thing to remember is that even if you have trouble imagining how the data is arranged, you can probably still make the math work. So back to our earlier examples, if we had a separate value for each color channel of each pixel of an image, we could store those as a 3-dimensional tensor, with separate planes for red, green, and blue values. For these lessons, we'll mostly talk in terms of scalars and matrices. When we use vectors, we'll just think of them as matrices too, where one of their dimensions is size 1. For example, when considering these length 3 vectors from earlier, we would say this row vector is a 1 by 3 matrix, and this column vector is a 3 by 1 matrix. We'll also sometimes need to refer to individual elements inside a matrix. We do that using its index, which is its row then column. So if this matrix were named A, its values are located at these indices. The indices of the locations in the first row are A11, A12, and A13. The locations in the second row are at indices A21, A22, and A23, and so on. So we'd say the value at A32 is 8. One last thing I should mention. In math books, things you read online, even most of the things you read in this class, indices usually start at 1, like I've shown here. See how the first row is row 1 and the first column is column 1? Counting from 1 makes perfect sense, but in programming languages, it's more common for indices to start at 0, which looks like this. All the indices are just 1 less than you might expect. So in code, instead of that 8 being at index A32, we'd say it's at index A21. If you've got some experience writing software, you're probably already used to this, so just keep in mind that most written materials index from 1. But if you're new to programming, it's almost certainly going to take you some time to get used to counting from 0.